5.1a addresses interpreting probability as a long-run relative frequency. What do you know about probability before we even begin? So let's look at this scenario. According to the Book of Odds, the probability that a randomly selected U.S. adult usually eats breakfast is 0.16. Explain what that actually means in this setting. So how would you define that probability? A nice, clean way to define it would be say something like this. If you ask a large sample of U.S. adults whether they usually eat breakfast, about 61% will answer yes, is one way you could define this as probability. Part B, why doesn't this probability say that if 100 U.S. adults are chosen at random, exactly 61 of them usually eat breakfast? The key here is why aren't they using the word exactly? Well, you have to be careful because exact will actually vary from sample to sample. This particular probability was generated off a random sample. The next thing, what probability means, is actually what we expect to happen, not what is actually exactly going to happen. Let's look at number 2. Probability is a measure of how likely an outcome is to occur. Match one of the probabilities that follows with each statement and defend your answer. So we have these 4 scenarios, but we have up here 6 different options to choose for the probability. Which ones of these options best go with this scenario? Scenario A, if the outcome is impossible, it will never occur. So if it's impossible, it will never occur would be a probability of 0. So we've used that one. Part B, the outcome is certain. It will occur on every trial. If the probability is guaranteed to happen, it's going to be a probability of 1. Part C, the outcome is very unlikely, but it will occur once in a while in a long sequence of trials. If it's very unlikely, in this case, I could see either looking at one of these 2 options. But very unlikely to me would be even less likely, so I would say the 100th on there, or 1%. And the last one, this outcome will occur more often than not. More often than not means more than 50-50. So if you look at the 2 that are left here, 0.6 or 0.99, the 0.6 would better represent more often or not versus the 0.99, which is close to almost exactly every time. Put yourself in this scenario. Suppose 4 of you get together to study for the next AP test. When you leave, every person ends up grabbing the wrong book. How likely was it that not one person got the correct book in this right scenario? So what we have here is we have 4 different books. Each of them has your name in it. What's the probability not one person of the 4 of you grabbed the correct book? This is actually a pretty challenging first probability question for you. So a method I'm going to show you to figure this out is called a simulation. Simulation is considered to be a very powerful tool when trying to model chance. You use it when the theoretical probability is hard to do. So we have a little scenario here I just want to walk you through on how you could simulate this actual situation and try to estimate to the best of your ability the correct answer. So this right here is the scenario I already set up about the 4 books. Let's talk about how you could simulate this. Step 1, what you could do is on 4 equally sized slips of paper, write the numbers 1, 2, 3, and 4 to represent your books. Then in step 2, shuffle the papers, lay them down one at a time in a row. If the number on the paper matches the position, this represents the student chose their own book. And then count the number of students who get their correct book and record that. Step 3 says repeat this several more times, recording the number of students who got the correct book on each trial. So let's imagine I have my 4 slips of paper in a hat. I pick out the first one and I lay it face down. I randomly go in and I choose a second one and I lay it down, the third one, and then the fourth. This is position 1, 2, 3, and 4. If I reveal the results, here's what we're going to see. The first card shows a 2, which means it's a second student's book, and it's in the first position, so the correct person did not get their book. This next one here actually shows up with a 3, shows it's the third book, but it's in the second student's position. This guy here is going to show up with a 1, and then the last one would be a 4. So in this case, what would we record is that one student actually got the correct book, and that happened to be the fourth student. If we run this simulation 30 times and record this on a dot plot, here's what you might see. In this simulation, we see all 30 trials and how many times they happened. Remember the initial probability question. What is the chance that nobody got the correct book? If you look at that on the dot plot, you're going to see that it's going to be represented by this bar here. In this case, there are 11 outcomes. So 11 of the 30 is going to be an approximate probability to our question. And as a percentage, this is approximately 0.37. So roughly 37% of the time we got through a simulation. Now let me talk about the true theoretical probability on this one. If you look at here, I have actually represented all the possible scenarios that could happen. In this case, what you're going to see in this first example is you have the first person gets the first book, the second gets the second, the third gets the third, and the fourth gets the fourth. By the way, everyone got the correct book in here. But what if we start to mix it up? If we do, where maybe the first two get the correct book, but the last two don't, it could look like this. If you write out every single scenario, you're going to see that there's not 24 different outcomes for this. Now, which ones represent no one getting the exact book? The ones that I circled here are going to represent all 9 that actually meet this qualification. So the theoretical probability on this is actually 9 out of 24. Now I will tell you the AP board is okay for probability if you do not simplify the fractions. You could keep 9 out of 24, or we could actually simplify by pulling out a 3, so that would be 3 out of 8 is the probability. To make that consistent with our simulation, when you put that as a decimal, it's going to become 0.375 as the actual theoretical probability. What's pretty amazing about simulation is the one that we actually did, we ended up getting 0.37 as the simulated probability. Now remember, that was just our one sample of 30. It may not always be exactly that close. The more trials you do, though, the closer you will get to the actual theoretical probability. Let's formally define probability. It is a number that is between 0 and 1, and it describes the proportion of times the outcome will occur in a very long series of repetitions. So this is actually a pretty important part of it, that it's in a long term. It doesn't mean on the short run. Again, in our simulation, we got really close after 30 trials. Maybe we wouldn't have. Maybe we would have had to do it 100 times so that we did it in a very long series of repetitions. So a good way to actually say that is also to say this. It is the predicted long run relative frequency. Remember, relative frequency is just the percent of the counts, which is just a percent or a proportion. Another vocab word we're going to encounter is called the law of large numbers. And what that says is as we observe more and more repetitions of any chance process, the proportion of times that a specific outcome occurs approaches a specific value. And that value is actually referred to as the theoretical probability. I will caution you, if you are asked to define probability on the AP exam, somewhere in your definition you must talk about that this happens in the long run and not in the short run. Here's actually a nice graphical relationship of our 4 books example. In this case, they actually did 500 trials versus we did 30 in our simulation. Notice they stated here the correct theoretical probability is 0.375. That is the blue line in each of these. Now this right here is a simulation where they did up to 20 trials. And you're going to notice the average here is showing that the proportion is above 40%, which we know is too high after 20 trials. But as you run it more and more, what's going to happen is you're going to start to see that the things are going to average out to become the actual theoretical probability. So again, the rule here is if you do a simulation, you want to do enough trials so that their simulation can kind of calm itself down and actually become, on average in the long run, the theoretical answer. Now, I think this is a great common mistake that the AP board points out, and be very cautious of this. Students sometimes report probabilities as greater than 1. That's impossible. It's between 0 and 1. And the reason is this. If you put something in your calculator and it shows a number of this format, you must be very cautious. This is scientific notation where it says move the decimal point 8 to the left, which would actually make this number have 7 zeros in front of it, and then it's going to be this with the digits. Technically, this is going to round to approximately 0. Let's start a totally different example. What if we roll 2 dice? If you roll 2 dice, this picture right here shows you what the actual sample size looks like. Now, let me show you a really good way to figure out how many outcomes are in a total scenario. Here we're going to roll 2 dice. So I'm going to do die 1 and I do die 2. How many outcomes are there for 1 dice? Well, there's 6. How many outcomes are there for the second die? Well, there's 6. If you count this, you're going to see that there's 36 possible outcomes. Where are they getting that from? They're just multiplying these two together like they're a string. It is going to be die 1 and die 2. A lot of the times when you hear and in probability theory, it means to multiply. This is a wonderful, easy trick to use to figure out how many outcomes there are in the full scenario. Okay, so we have that right now. Here's the question. What is the probability of getting a sum of 7 when rolling 2 dice? They're saying that it's 1/6. First of all, let's just highlight where that comes from. The sum of 7 could be this. It could be 5 and 2, 4 and 3, 3 and 4, 2 and 5, and 1 and 6. Be very careful with probability theory, in particular with dice. Notice 6 and 1 and 1 and 6 are counted twice. They should, because this is die 1 and that's die 2. So be cautious of that. Now, you do want to make note, though, what if there's doubles? What if they had asked me about the sum is 6? Well, look here, the sum of 6 is 3 and 3. Do you see 3 and 3 showing up more than once? In this series, you're going to notice that the sum of 6, if that were the question, shows up here, 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 and here. Never do you see doubles being repeated in dice theory. Okay, back to the original question. They want us to interpret the value of 1/6. So all we need to say is something like this. We predict that after a large number of rolls, the proportion of the sum of 7 will be about 1/6. Here's an example on extended warranties. How much should a company charge for an extended warranty for a specific type of cell phone? Suppose that 5% of all the cell phones under warranty will be returned and the cost to replace is $150. Okay, so how much should the company charge? Well, first thing they should do is maybe make note of this. If they knew which ones would go bad, they would just charge those phones, right? But they don't. It's a gamble on which phone is going to go bad. So the easiest way to figure out what they should charge for the warranty is just take the probability of the 5% times $150, so about $7.50 to charge at least that much for the extended warranty. They could charge more, but to cover their estimated costs, a minimum charge of $7.50 would be warranted. Now here's a scenario about flipping a coin. Which of the following outcomes is more probable? So you're going to notice here they flip the coin. It looks like 6 times in this scenario and 6 times in this scenario. And they want to know which one is more likely to happen. Would you say both are equally likely to happen, neither is likely to happen, or the first one or the second one in this case? Well, think about it when you toss a coin. This first position has a 50-50 chance of heads or tails. So does the second, so does the third, and so forth. So in this case, these two scenarios look different, but they both have an equally likely chance of happening. Remember here, in each toss, heads and tails are equally probable. You have to be careful about what's called the myths of randomness. Probability says randomness is predictable in the long run. We could do a simulation, right? However, our intuition about randomness tries to tell us that random phenomena should always be predicted in the short run, but it's not. Let me show you an example where people tend to get confused with this myth of randomness. Here we have a hitting streak example. Suppose that a basketball announcer suggests that a certain player is streaky. That is, the announcer believes that if a player makes a shot, then he's more likely to make his next shot. As evidence, he points to a recent game where a player took 30 shots and had a streak of 7 shots in a row. Now, is this evidence of streakiness, or could have it occurred simply by chance? I mean, he got 7 shots in a row. Was he just on a streak? Well, let's further define one thing. Assume that he makes 50% of his shots and they do not depend on the previous. So this is actually important, that they're not dependent on each other. Well, if you do that, you could go ahead and you could actually run a simulation. And I did a simulation that actually flips a coin. Because if his shots making is 50-50, if I flip a coin 30 times to simulate his 30 shots that are being made, I'm going to do that and look at the simulation and see if there's ever a time where I see 7 shots in a row. And if I run that for 50 trials. So flip the coin 30 times, 50 individual times, and record how many the longest streak that you see. So here's what I did. This dot plot right here shows out of 50 trials how many times the longest streak showed up. And remember, we are talking about making 7 shots in a row. How likely is it that he made 7 shots, or even more, really? Well, if you look at the dot plot here, 7 shots or more out of our 50 trials comes up with 7 times. Well, if you do 7 out of 50, that's going to be a 14% chance that it actually happens. So based on that, do you think he's streaky, or is this by chance alone that it happened? Well, 14% is somewhat of a likely chance, so in this case, we could say it is somewhat likely to happen. However, be cautious and think about this. In each shot, the probability to hit or miss is 50%. So it is another thing simply by chance that it ends up being a streak of 7. Even though we're seeing there's a 14% chance in this simulation for it to happen, it is still 50-50 each shot if he is going to make it. Now let's assume that this player makes 48% of his shots. So he's not quite as good. And the result of the shots don't depend on the previous shots. So if he did one well, doesn't necessarily mean he'll do the next one well. How likely is it this time for the player to have a streak or 7 or more shots in a row? The question is it more or less likely than what we saw in part A? Well, the probability of him making it now is actually lower for each shot. So based on that, it would be less likely for him to make a 7 streak in this case versus if we looked at part A of this question. The last thing I want to talk about is the law of averages. When the shooter in a dice game of craps rolls several winners in a row, some gamblers think he has a hot hand and bet that she will keep on winning. Others say it's just this law of averages, meaning that she must now lose so that the wins and the losses balance each other out. So if she's on a streak where she's winning, someone's going to say, nope, she's going to lose next. Here's the deal. Here, in this case, the law of averages is actually wrong. In that we can't say what's going to happen to that one next shot just because they're on a streak of winning means they're going to lose. But what we do know you have to be cautious of is that outcomes do even out in the long run, because that is what theoretical probability is that you will work your way toward the actual theoretical probability as you do the trials more and more times. This is actually kind of a good thing to be cautious about with the law of averages in this example. It says, belief in this phony law of averages can lead to serious consequences. A few years ago, an advice columnist published a letter from a distraught mother of 8 girls. It seems that she and her husband had planned to limit their family to 4 children. Well, when all four were girls, they tried again and again and again, thinking, of course, we're going to have a boy next. After 7 straight girls, even her doctor had assured her that the law of averages was in her favor, 100 to 1, thinking, yep, you're going to have a boy this time. Unfortunately for this couple, having children is like tossing a coin. 8 girls in a row is highly unlikely. But once 7 girls have been born, it's not at all unlikely that the next child would be a girl again, and it was. There's always still 50-50 chance for that next one trial. So be cautious when you're reading scenarios about the law of averages. However, if they're talking about in the long run, which is just the probability, keep in mind, given enough trials, events with the same likelihood will even out in the long run. And you will get, on average, your family could consist of, 50-50 boys and girls. But these folks are going to have to keep having more and more children for that to happen. They're going to have to do a very long run trial. Red is due example wraps it up nicely. In casinos, there is often a large display next to every roulette table showing the outcomes of the last several spins on the wheel. Since the results of the previous spins reveal nothing about the results for the future spins, why do casinos pay for these displays? Because people aren't that smart all the time. The thing is, they're trying to deceive you. Many players use the previous results to determine what bet to make. They are assuming the law of averages, that it's going to kick in. The next one has got to be that other number that hasn't shown up. But it doesn't matter. In that next spin, every number has the same probability of showing up again. So don't be tricked by the world, because they might be trying to trick you and deceive you, in this case, so the casino can make some money.